Hey there, coming at you from West Virginia. So, it's time for Joke of the Day because it is the best part of the day. And my joke today says, why can't your nose be 12 inches long? Because then it would be a foot. Alright, enough horsing around, enough silliness. Let's take a look at the complement of an event. Thank you, JD, for that intro. So the complement of an event deals with probability. And if we're talking about the probability of an event, then we have this symbol that denotes that. Every time we see this symbol, P parentheses E, that tells us we're talking about the probability of that event. We have a new idea though. You can have the success of that event, the probability of it happening, or you can have the probability of it not happening, which loosely said would be your failures. So we denote that with this symbol right here. And notice these two are very similar. What's the difference between the two? Absolutely. This one has that little tick mark right there, that little prime notation. We call that a prime. So P prime E would be the complement of that event. In other words, everything but that event. And like I said, typically we think of that as our failures. So the idea here is this. If you've got the probability of that event, and you've got the probability of that of everything but that event, put the two together, that would be the entire sample space. And we know that the entire sample space has a probability of 1, meaning 100%. We know that probabilities are typically fractions, so they go from anything from 0, meaning something that's impossible, to a 1, which is something that's absolutely certain. So our probabilities range within this range of fractions. So if we take that entire sample space being a 1, then that means that if we take the probability of an event and we take the probability of everything else, that has to total that sample space. So here we have the probability of the event plus that complement, everything but the event. That will give us our sample space of 1. Another way of looking at this is say, what if we have the entire sample space and we take out the probability of the event? In other words, we take out the successes. Then what's left over but those failures? In other words, that complement. So if we take our entire sample space of 1 and we take out the probability of that event, that leaves us with the probability of the complement, or in other words, those failures. These two formulas are very helpful whenever we're dealing with complements of an event. So let's take a look at our first example that says, if we have a card that's drawn from a standard 52 card deck, and I've got a standard 52 card deck here with me, we want to know what's the probability that it is not a spade. Well, if you're not familiar with cards, there's certain things that you need to understand about cards. The first is that you have 4 suits. One of those suits is clubs, and here's the symbol for clubs. We have spades, and here's the symbol for spades. I'm not very good at drawing this. And we have hearts and we have diamonds. Now, if we have hearts, they're going to be red. And if we have diamonds, they are also red. So in other words, we have 4 suits, 2 of them black, 2 of them red. If there are 52 cards and we divide them by 4, that means there's 13 cards in each suit. So I have 13 of these clubs, 13 of these spades, I'm going to have 13 of these hearts, and 13 of these diamonds. All of them range from ace to king. So I have an ace, I have a king, I have a queen, I have a jack, 10, 9, 8, 7, 6, 5, 4, 3, 2. And that is all the 13 cards that are in each suit. So if I'm dealing with this situation where I want to know what's the probability that it is not a spade, well, remember that's going to be all these clubs, all these hearts, all these diamonds, and every card in them. So I could add them all up, but sometimes it's faster to go with the idea of the complement. In other words, it would be easier to go with this concept right here. And let's take that entire sample space of 1, 100%, take out the probability of the event. In other words, what's the probability of actually pulling a spade? Well, first we have to look at that concept. So the probability of actually pulling a spade, doing a rough job there of drawing that spade. Success over total, remember that's your definition of probability. I want success over total. Successful ways to pull a spade, well, there's 13 of them there. Now my total is all the cards that are in this deck, as you can see. 52 of them. And you can see, sure enough, as far as the spades goes, I do have 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and my Ace. And that is the entire suit, all 13 cards of those spades. So I've got 13 out of 52. That is my probability of a success. Always simplify a fraction if you can, and 13 out of 52 simplifies to 1/4. And so now I'm going to use this idea of that complement to be able to figure it out. So I'm going to say, let's take that entire sample space of 1. Let's take out that probability that I'm talking about. That will give me the complement that I'm looking for. And if I take 1 minus 1/4, that gives me 3/4. So the probability of pulling something that is not a spade will be 3/4. Okay, let's take a look at a couple more examples. All right, get this craziness of under the sea out of the way. I gotta get my flippers out of the way so that I can turn this thing. No scuba diving for me, I'm too busy teaching. So, let's take a look at another situation. In this situation, it says I have 2 dice that are being rolled. I need the probability that the total showing is less than a 10. Well, first I need to figure out that entire sample space. Now recall we talked before how to get a sample space. It's by using that fundamental counting principle, because it'll be too difficult for me to list all this out, because I could roll one die and come up with a 1 and the next one be a 1, or I could do a 1 and then a 2, and I could do a 1 and a 3 and a 1 and a 4, a 1 and a 5, 1 and a 6. I could do a 2 and a 1, 2 and a 2, 2 and a 3. This is getting exhausting already. So I think what I would prefer to do is use that fundamental counting principle to come up with the total number in the sample space. I don't care that much what's in the sample space, just how many, so that I know when I'm talking probability being success over total, I know what that total will be. So using that fundamental counting principle says, okay, how many slots am I dealing with? Well, I roll the dice once, I've got 6 possible outcomes. I roll another dice, because it says I have 2 of them, I roll the other dice, I've got again 6 possible outcomes. I'm going to multiply those 2 numbers together, and that tells me that I've got 36 total outcomes when I roll 2 dice. If I was to list all this out, I would come up with 36 items in there, 36 events in there. So now I want to look at this and I say, this is my total in terms of probability. But I want to know what's the probability that that total showing is less than a 10. Well, it would be a little exhausting to count all these up. So I think instead I'm going to use that concept of that complement of the probability. In other words, I'm going to say, what if I take that entire sample space of 1, I take out the probability of the event, that will leave me what I'm looking for, which is the complement. So the event is being that it's going to be less than 10, and that's actually the event. But what I'm going to do, I'm going to say, let's look at the opposite of that. I'm going to take that out. Perhaps instead of writing it this way, I should say, let's look at the probability of the complement, and that'll give me the event itself. They're one and the same, basically. So now that complement, instead of saying that it's showing less than a 10, complement would be 10 or more. 10 is okay because this says less than 10. Anything smaller than 10. Everything totaling up to a 9. Totaling 10 or more is going to be that complement. So that complement of that event then is going to say, yet again, here is my formula for probability, success over total. I want to know, in this case, what are my successes? Well, now my successes are going to be 10 or more. Well, remember, in terms of that, that would be, for instance, like a 10 or more would be 5 and 5. That would be 6 and 4, or 4 and 6 is okay. That would be 5 and 6, or 6 and 5 would be okay. Or 6 and 6 would be okay. So in other words, these are the ways that I can total 10. These are the ways that I could total 11, and this is the only way that I could total a 12. So that gives me 2, 4, 6 ways that I can come up with that complement idea. So 6 ways out of 36 total outcomes. So in terms of this formula here, what I'm going to do is I'm going to say, well, now it's 1 minus, and again, that probability of the complement is going to be 6 out of 36. Always simplify a fraction if you can. This simplifies to 1/6. So I'm going to take that 1/6 out. That will leave me what I'm looking for. And if I take a 1 minus a 1/6, that gives me 5/6. That's the probability of when I roll those two die, the total showing will be less than a 10. Now let's look at our last example. It says if 5 coins are flipped, what is the probability of obtaining at least one head and at least one tail? Well, again, I need to create that sample space. So what happens here is I'm saying, well, I flip one coin. What are my outcomes? Heads or tails? That's the only thing that can happen. I flip my second coin. What are the only outcomes? Heads or tails. I flip my third coin. The only outcomes are heads or tails. Flip my fourth coin. The only outcomes are heads or tails. And flip my last coin. The only outcomes are heads or tails. So now I'm going to multiply all these together. Fundamental counting principle happening here. That gives me 32. So I have 32 total outcomes here. That's my entire sample space. Now let's look at this idea that I want to know the probability of attaining at least one head and at least one tail. Once again, being that there's 32 outcomes, this would take a long time to list all those outcomes and count it up. I think what I would rather do is use this idea of the complement, and let's take out that complement, and that'll give me what I want, which is the event itself. So the complement concept here is something that is not at least one head, not at least one tail. The only way that could happen is to have all heads or all tails. That's the only way to not make this happen. So I'm looking at that complement being, what are the chances of all heads or all tails? Well, how many times can I make this all heads? It would have to be head, 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 head. There's only one way to make that happen. But what's the chances of making it all tails? That would be tails, 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 tails. There's only one way to make that happen. So in terms of this complement, the success is being all heads or all tails. There's only 2 ways that I could be successful out of that, out of 32 total outcomes. Now here we are again. Always simplify a fraction if you can. 2 goes into both 2 and 32. It goes 1/16. This is the probability of that complement. So I'm going to take my entire sample space. I'm going to take out that probability of that complement, and that will give me what I want. And when I take a 1 minus 1/16, that gives me 15/16. That's the probability that I will flip at least one head in it and at least one tail in it when I flip all 5 coins. So I hope that that helps with the idea of the complement of a probability, and have a great day.